In this lesson, we're going to be taking a look at graphing exponential equations, specifically with bases other than 2. Up until this point, we have graphed a number of different problems where we've graphed some variation of y equals 2 to the power of x. But it was always that 2 is our base. But exponentials actually can be graphed with anything in their base. So today we're going to be seeing how that changes when we change the base. So our first example that we're going to be looking at here is y equals 3 to the power of x. All right, so we're going to start plotting some points. For my first point, I'm going to go to 0. What is anything to the power of 0? Hopefully you're saying 1 right there, because anything to the power of 0 is 1. And so this is going to start up there at 1, just like 2 to the power of x did. Next up, if x is 1, 3 to the power of 1 is 3. If x is 2, 3 to the power of 2, that's 3 squared. So that's 9. And you can see that's going to be the last one I can plot on the right-hand side there before I run out of room. All right, and so as I take a look at what was happening to those points, you notice I was up 1, and then I was up 3, and then I was up 9. What was I multiplying the height by every single time? 3. And so when it was 2 to the power of x, we doubled our heights as we went to the right. When it's 3 to the power of x, you multiply each of the heights by 3 each time you go over 1 to the right, which then can tell you what we're going to be doing as we go off here to the left. Because if I'm multiplying by 3 as I go to the right, I'm going to have to be dividing by 3 as I go to the left. So if I go left 1, I'm going to be up a grand total of 1/3. And then my next point over to the left is going to be up 1/3 of that, which is actually at 1/9. And then 1/3 of that is actually 1/27. Now we're getting very, very close to 0. And if I divide that by 3, that's 1/81. Again, very close to 0. And then after that, even closer to 0. But notice we're never actually going to hit 0. And so just like 2 to the x, my graph of y equals 3 to the x also has an asymptote here at 0. And so yes, we'll go ahead and we'll draw that in. Every single exponential, regardless of the base, will have an asymptote here at 0. And so this is our final curve of our graph. Now the other layer that we're going to be throwing in today is what happens when we multiply our exponential equations by something. So here we have the graph, or the equation rather, 2 times 3 to the power of x, and we're going to make the graph for that. Well, we just graphed 3 to the power of x. And so we saw that it included these points. Well, what does the 2 out front do? Well, we hopefully already know that answer because we've seen a lot of graphs this year with a number like that out front. So for instance, we have seen graphs like 2 times the absolute value of x, or 2 times x squared, or 2 times the square root of x. We've graphed all of those. And in all of those cases, that 2 that was multiplied out front always made it steeper. We said that was a vertical stretch by a factor of 2. In other words, what it did is it doubled how tall this thing was. And the same thing is going to happen with our exponential here. So like this first point that we plotted here at 1, its height is going to double. Now when I talk about its height, I mean its height from the asymptote. And the asymptote is not going to change in this case. The asymptote is still at 0 because the whole thing has not been shifted up or down at all. There's no vertical shift. It's only a stretch. A shift would require adding or subtracting. All right, so then instead of going up 1 for my first point, I'm going to go up twice as far, which is up 2 there. My next point here, that was up 3. I again need to double how tall that is. So I'm going to double that height up to 6. And then the next point was up 9. If I doubled that, that thing would be way up here at 18. Now something I want you to notice about these though, is I went from 2 to 6 to 18. Notice, once I knew where that starting point was there at 2, if I multiply the 2 by 3, I get 6. If I multiply the 6 by 3, I get 18. So just like when we graphed the first one, the parent function, I was tripling my height as I went to the right. I'm still tripling the height as I go to the right. Really, the only thing that the two did is it changed the starting value. That is, it changed the y-intercept. And that's it. And if you just remember what the pattern is after that, you can plot the first point and then cruise from there. And so if I were going to be making this graph from scratch, the very first thing I'd do is I'd draw my asymptote down at 0. Then I'd notice that I'm multiplying by 2, so my first point is up 2. And then as I go to the right, I'm going to triple that height. So 2 times 3 is 6. 6 times 3 is 18. That's off my grid, so I don't need to plot that point. Now I go to the left, where I'm going to be divided by 3 again. And so 2 divided by 3 is 2/3. And then I can even just eyeball what a third of each of these heights is as I go over to the left. And that gives me a pretty good idea about what that graph is going to look like. And so then we're able to draw in our entire graph. Now, just in case you were thinking that this was all going to be nice, smooth sailing, let's throw a fraction in there. See if that might throw you off a little bit. Hopefully it won't, though, because as you'll see, it's actually pretty similar to what we've been doing. So, what's anything to the power of 0 again? 1. That includes 1/2 to the 0. That's also going to equal 1. So my first point is still at 1. That didn't change at all. Now remember when it was 2 to the power of x, I doubled the height as I went to the right. When it was 3 to the power of x, I tripled the height as I went to the right. So in this case, I have 1/2 to the power of x. And as you might expect, that means we are going to half the height as we go to the right. So where I started at 1, I then would go up half as far for my next point. And then half as far as that for the next point after that. And so on and so forth all the way down. So as I go to the right, I'm dividing by 2. What do you suppose we're doing as we go to the left then? Well, the opposite of dividing by 2 is multiplying by 2. So I can take my 1 and multiply it by 2 to get 2. That times 2 is 4. That times 2 is 8. And notice this looks just like the 2 to the power of x graph that we've worked with in the past, except it has been flipped over the y-axis. That is, where it was going up, it's now going down, and where it was going down, it's now going up, but all the amounts are exactly the same as 2 to the power of x. And as you can surmise then, seeing what the graph looks like, yes, it does have an asymptote still at 0. So you've now seen all the little variations. You should be able to graph this one on your own. I would like you to try doing it on your own first, and then follow along here as I work through it together here. So the 6 out front, that is changing my first point. So instead of my first point being at 1, my first point is going to be up at 6. All right, then as I move to the right, I'm going to be up half as far each time. So half of 6 is 3. Half of 3 is 1.5. Half of 1.5 is 0.75. You might even just be eyeballing this to say, well, that looks like it's about half of that. This looks like it's about half of that. And very quickly you can eyeball these graphs in terms of just cutting each of those heights in half. So as I go to the right, I'm cutting in half. As I go to the left, I would then have to double my heights. Well, doubling 6 would put me up at 12. If your graphing grid goes out to 12, by all means, plot it there. But mine doesn't, so I'm not going to. And so this is then my final graph for this particular problem. All right, next up, we're going to be taking a look at this, 4 times 1.5 to the power of x. This is not the sort that you're going to be asked to graph by hand very often. However, it is one where I want you to know where these types of graphs come from and how they get made. Because a lot of the graphs we see actually used to represent real data and real equations that are taking place, they tend to have decimals in their bases. First thing I want you to recognize here is that there is no addition or subtraction taking place, so the asymptote isn't moving, which is why it'll still be leveling out close to 0. It's always going to be getting close to 0, but never actually crossing it. Now the first point. Shouldn't need anything fancy to know where that first point goes, right? Because normally my first point would be here at 1, but of course when I multiply it by something up front, it changes that first point. So my first point's actually going to be up here at 4. All right, Next up, as I go to the right, I'm going to be multiplying this whole thing by 1.5. Well, 4 times 1.5, that we can actually do pretty well. 4 times 1.5 would end up giving us 6. And then I can even break out the calculator and do 6 times 1.5, which would be 9. Those ended up being fairly pretty points. They very quickly are going to start getting not so pretty, though, as you would see, if you kept going past that. As I go to the left, I'll be dividing by 1.5. So notice, whatever I do to the right, if I'm multiplying, I divide by that same thing as I go to the left. And this is where our numbers can get kind of messy, because if I do 4 divided by 1.5, that actually ends up giving me 2 2/3. And if I divide that by 1.5, that ends up giving me 1 7/9. And we're very quickly into a place where these are kind of some ugly decimals. And so at least 2 points on both sides, that's usually enough to get a pretty good idea about how this graph is moving. So then you'd be able to sketch that in from there. But of course, as you take a look at this, these individual points, they didn't look that spectacular. They didn't tell us quite as much because we're on such a limited scale. Well, let's take a look at one more real-life kind of equation. This is a very, very typical kind of equation that you might see. But of course, our normal -10 to 10 graphing grid that we tend to use in math wouldn't necessarily be so relevant here. So instead, we'd have to set up a bigger scale. Think about what sort of size would you need on each axis for this? Like for your y-axis, what do you need to go up to, do you think? Hopefully you're thinking of something that's way over 1,000. Because if I'm going to graph this, my very first point would have to be at 1,000. So we have to have room to be able to move up from there. And it's just going to be a matter of figuring out some other points along the way. Well, for that, if you're actually having to graph an equation like this by hand, which again, typically you wouldn't do, this is where you'd probably tend to use software in order to be able to help you make your graph, we could actually just graph a couple points here. So I'm just going to grab a couple numbers and then plug them into my equation. And if I do that, I end up with these points. And that gives me a pretty good idea about how this graph is behaving. And so then we can get the curve drawn through those. Now you'll notice that as I made this graph and set up my axes, I didn't include the negatives. That's because this is now looking at, okay, what would a real world equation kind of look like and how would it behave? And in real world kind of situations like this, usually our equation will not be 1,000 times 1.1 to the power of x. Typically, you actually find it to the power of t. And we'll, generally speaking, not be that interested in a negative time value because it tends not to be actually meaningful in a given situation. And so that's why all the more you're going to see these just looking at the positive values involved in the problem. So again, this one, it's not thrown in here because you're going to need to be making these by hand, but rather because I want you to know why these end up looking the way they do when you see them actually made for you.